All right, welcome to lesson 9.2. What we're going to take a look at today is graphs of polar equations. So I'd recommend you go to your digital classroom, open up instructions for 9.2. Specifically today, we will need some graphs. So I'm going to open up the pre-programmed graphs, which is between number 3 and number 4 here. You can open up, I would advise you to open up your lesson exam right here, that link. But let's open up this one that does most graphs so that we can be ready to go. All right, so number 1 asks us to graph the point S, which is -3, 60 on a polar grid. And just as a reminder, what that means when you see a -3 in the spot of R, so the radius here, it seems to be -3, which doesn't make much sense. How can you have a circle with a radius of -3? What that really means is to reflect on the pole. Reflect on the pole, which in this case is 60 degrees. So instead of going 3 units towards 60, so 1, 2, 3, where you might think it might be, we actually reflect and go the opposite direction. So I'm going to go 1, 2, 3, and this would be point S right there. So this point is not the correct location. It would be there. Another way of writing that point, if you looked at, let's see here, 1, 2, 3, is we could also label this as being 3 units on the pole 240. So that last lesson we dealt with writing points 4 different ways. And so I would say the most common way of writing that point would be to state it as all positive numbers, where you would just say it is 3, 240. That would be probably the easiest or the most efficient way of writing it, but there are other ways of writing it. There are a total of 4, and so here's 2 of them there. If you wanted the other 2, the way I think about it is if this point was on the third circle at 240 degrees, what that means is that 240 is calculated by going around the circle here counterclockwise. If you looked at the negative angle would be as if you looked at it going clockwise from the positive x-axis. So what is that angle there? That would be -120 degrees. Now, how do I know it's -120? Well, because there's got to be a difference of 360 here. And so if you just took your 240 and subtracted 360, what you'll get is a complete circle. So going this way all the way around would give us that -120. You can also see visually that it just is reflected. 240 and 120 reflect one another vertically. So that is also equivalent angle. So instead of just writing this as 3, 240, I could write this point as 3. I'm going to substitute the 240 with -120. And that would be a third way. And I'm also going to reflect this one. So a fourth way, let me just draw an arrow here so you can see, would be if I did the same idea with the 60 degrees. Earlier we had this value. Well, 60 degrees is if you subtract from 360, which is 1 full cycle around the unit circle here, you would end up with -300 degrees. So 60 is coterminal with -300, as you can see they're across from one another. And so if I just substituted the positive 60 with -300, this would be the fourth way of writing that point. So -3 stays, this becomes a -300. You could write each point 4 different ways, and that's how you could do it. Number 1, you don't have to do it all those ways. Now, if you wanted to graph this and you wanted some help from technology, on my calculator, if you go to calculator 28, plotting polar and rectangular coordinates, you could use this to graph the same problem. This is in polar form with a radius of -3 on the angle of 60 degrees. Check your mode. This is in the correct mode here. I'm going to zoom in just a tad. No, zoom this way. There we go. So it's counting by 1. So you can see it's 1, 2, 3. Third circle out. It's on this pole that goes through 240 degrees. So we did do that correctly. All right, let's try number 2 now. It says find 3 different pairs of polar coordinates that represents this point. So, okay, let's walk through this again. This will mean reflect on the pole. Reflect on the pole, that is -2 pi over 3. And so where is negative 2 pi over 3? This means I need to find the theta going clockwise. When you have negative angles, you go clockwise. And so this angle, so 0, 2 pi is all the way around. If theta is moving downward, that means theta is less than 0. And so what I'm going to do is I'm going to move my pencil this way, but I'm going to be reading off these values but putting a negative in front. So I'll say like negative pi over 6, negative pi over 4, but I'm going to be going this way. So this location is negative pi over 6. This is negative pi over 4. This would be negative pi over 3, negative pi over 2, negative 2 pi over 3. Notice that at this fourth value, that would be the value here. Sorry, fifth. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, the fifth one. So 4 pi over 3 is coterminal with negative 2 pi over 3. Notice if you add those up, if I added this across, I would end up with 4 pi over 3 plus 2 pi over 3, which would equal 6 pi over 3, also known as 1 full circle 2 pi. So that is the right value there. Okay, so there's that point. We found it. Or sorry, I didn't actually plot it yet. There's the angle to this spot there. That angle is negative 2 pi over 3. But it says to go reflect on the pole, so I actually go 1 away from it. So it'll be the pi over 3 over here. This is actually where that point is located. Okay, so this actual point is right there. I'm going to give it a name. I'll just call it A here, and I'll put A right there. Okay, so there's this true point. So point A, if I was going to label it all 4 ways, the easiest way would be to think of it in terms of positives. It's 1 unit on pi over 3. And I could also substitute that pi over 3 and say, okay, well, if it's pi over 3 going this way, what would it be going all the way around? Well, it would just be negative 5 pi over 3. How did I get that? Well, because if you count it all the way around here, that negative 5 pi over 3, that's the distance it would have to take going this direction to get to A, going all the way around. So you go all to these values, but you'd be counting these with the negatives in front. Since those two are vertically reflected, it will be that point, negative 5 pi over 3. So this 1 comma pi over 3 is the same thing as 1 comma negative 5 pi over 3. Because negative 5 pi over 3 and 1 pi over 3 are coterminal, these two spots happen to be equal. Now they already gave us this point up here, negative 1 comma negative 2 pi over 3. And we found out that coterminal with negative 2 pi over 3 is 4 pi over 3. So if I just substitute that there, I'll have my last point. So I leave this radius as negative 1, but I'm going to change the angle to 4 pi over 3. And now I have all 4 listed out. Let's check and make sure I plotted that in the right location. So this time the magnitude would be negative 1. My angle is negative 2 pi pi divided by 3. I need to change my mode. So I hit the wrench up here. I'm going to hit radians. And it is, in fact, located just there like we thought on pi over 3 pole, 1 circle away from the origin. All right. Let's take a look now at number 3. What is the distance between these 2 points? So 2, 150, second circle at 150 on the pole 150 degrees. So 1, 2 is right there. It's a circle with a radius of 2. We have this point here. And 4 at negative 45 degrees. So here's 45 if you're going positive, but we're going negative 45 degrees. Which would mean it would go down here at 315. That is equivalent to negative 45 degrees. And this circle is going to be located on circle number 4, or circle with a radius of 4, I should say. So we want to know what's the distance between these 2 points from here to there. And so I did give you a formula last class. If you want to do the algebra, the distance formula, it is derived from the law of cosines. It's going to be the square root of r1 squared plus r2 squared minus 2 times r1 times r2 times the cosine of theta 2 minus theta 1. If you want to do it by hand, that's the formula you're using. I did create a calculator for it. It is calculator number 30, polar distance. And so in this one, I plug in my values. My radius was 2, or my magnitude was 2, and the angle is 150 degrees. My second point, I had a magnitude of 4, or radius of 4 at negative 45 degrees. I'm making sure I'm in my right mode. I'm seeing a bunch of degrees, or if you click the wrench, you'll see it's in degrees. So this is graphed correctly. The distance is 5.95 approximately. Now they don't have units here, but since it's distance, I'll just say 5.95 units. All right, with that, we're going to take a look at some graphs of polar equations. So we're going to have some new names: cardioids, limicons, limniscates. That's what I call that. I think it's more like limniscate, but I call it limniscate. You're also going to have roses and a spiral that we're going to see today, as well as circles. So here's just kind of overview of some equations and some rules on all of this. What I want you to know is the difference between what's going to be called a limicon, and a cardioid. A limicon is going to have this little inner loop, as we see today. So I think of limicon comes with a loop, lima with a loop, limicon with a loop. And then cardioid, it's going to kind of look like a butt. And so I've heard students say, you know, you need to do some cardio to work on that butt. And so when you see that butt, think it's going to, you need to do some cardio. Other students are going to say one that's vertical, this one's horizontal, is they're going to say, it kind of looks like a heart if you turn the shape. And so again, if you do some cardio, it'll strengthen your heart. So either way, that works well. So there's those two shapes, very similar equations, very similar equations. It just has to deal with the A's and B's, whether they're bigger or the same value. We're also going to see roses today. And limniscates, it looks like an 8, makes it easy. Limniscate looks like an 8, rhymes. And then we'll see spirals, as well as circles, if I didn't mention that already. All right. And we'll talk about some symmetry as we go along. So this symmetry that we specifically are going to be talking about is whether it's with the line pi over 2, whether it's with the polar axis, or I should say not the line, I should say the pole pi over 2, or a symmetry with respect with a different pole coming through. So we'll see that as we go along. Quickly, before I move on, some of the rules here. It says if you have a function of cosine, then that'll be symmetric with the polar axis, meaning the x-axis will cut in half. If you just think about sine is y, cosine's x. So the x-axis, the polar axis would cut in half. If you have a function of sine, the y-axis, sine is y. The y-axis will cut this in half, or the pole pi over 2. If you have a function where you have a value or transformation inside in the parentheses, so like cosine 2 theta, something like that, that will do some algebra as well to figure out where the line of symmetry is. And that's how you can also have it with the pole. Or you can see some with, when we get here to a limniscate as well. So here, this first one, it says graph 3 cosine. Now I have a calculator for you. I know this is a very basic equation, but I still create a calculator because it's going to help us as things get more complex. So it's calculator 29 here. Mine's starting off as a rows, and so I'm going to graph this. It says r equals 3 cosine. So r equals 3 cosine of theta. And what I want you to see is down here, right below it, it says copy and exchange the r with the r1, which I've already done, but you're going to copy the rest here. Copy that. And my computer froze on me. And I'm going to paste it here. But what I'm going to do is after this theta, I'm going to hit a 1. And so what this is going to do is going to help us later on finding specific values depending on what theta is. So you can see this is a circle. It's a circle that goes out with a radius, or that extends out as far as 3, and it starts at the origin. So this circle doesn't actually have a radius of 3. If I zoom in, you'll see that it extends to 3, but the radius would be from the center about 1.5 to 3. So the radius is actually only 1.5, not 3 units. So let me put this on my graph here. A circle that is 1.5 and its radius, so something like that. That would be the graph here. Okay, so now I want to show you the theta. This is kind of a neat little tool here. As you see that as theta changes, you get to see how it traces this graph. So the graph actually starts on the far right over here. If you think about the unit circle, how theta starts on the far right, it starts over here on the far right and it curves around. The reason this graph goes right is because it's dealing with cosine. And so when cosine has an angle of 0, cosine of 0 is actually 1. And so the math that takes place is it takes 3 and it multiplies it times 1, and it gets that value at 3. Now, as theta gets closer and closer, when it gets to pi over 2, cosine of pi over 2 is 0, if you remember your unit circle. So I'm going to put right here pi divided by 2. When you get to pi over 2, you'll see that I get a 0 here because cosine of pi over 2 is 0, and 3 times 0 is 0. That's why it's going to come to that point. So everything in between is how it just graphs all the way around to find the value. So if you're watching, now if you're wondering, how is it going downward? If cosine is positive, negative, what's it doing? Well, this is with a negative r value. So here, the theta is actually, let me just type in 2 pi over 3 so you can see this. At 2 pi over 3, when theta is 2 pi divided by 3, we would think that that should be graphed over here on this pole. But notice it's not. It's moved this direction because our r value is negative. So instead of moving towards 2 pi over 3, it's moved away from it 1.5 units. If I zoom in, you can see that's right at like 1.5. There's one circle. Here's 2 circles. It's right in the middle of it. So that's kind of how polar graphs work. They're very interesting to see and to play out. All right, back to our notebook file here. Let's try for sine. And so let's see the difference when I go to for sine. So for sine, what that does is it's going to move my graph vertically because sine is y. Sine has to deal with the y component. And again, it's going to extend as high as 4. I say again, last one extended to 3, but the coefficient was a 3. This time my coefficient's a 4, so it will extend as high as 4, but it's only going to go as low as 0. Now you might be thinking, well, what happens when I'm working with these negative or these theta values that are down here? Shouldn't the graph be placed down here? Well, let's see. If I put in a theta, let's just say 4 pi over 3, we would think that the graph should be placed somewhere on this pole, and technically it is. But the math, if you put in 4 pi over 3 right here, or in this location here, these are the same equations, you'll notice that the radius is negative. So instead of moving negative 3.46 this way, moving negative means you go the opposite direction. So it's 1, 2, 3, and some change to get you to that point. So all the values that are down on the underneath side of this graph, these thetas, must have negative r values, and thus they're reflecting on this side of the graph. So let's go ahead and plot this one now. This would be a circle with a radius of 2. Circle with a radius of 2. How do I know it's a circle with a radius of 2? Because it extended as high as 4 and it touched the origin. So the radius is 2 there. All right, and now let's see this problem. Well, it says graph r cos theta equals 4. What I'm going to do is actually get this set as equal to r. So since this is multiplying, I will divide out the cosine here. Like that. And so what I'm going to actually graph is r equals 4 over cosine theta. Let's go see what happens when I do this. And I'm not actually sure if I could, I might try it first. Let's see if I could have typed it in. Cos theta of 4. I'm not sure if this will work. Oh, it does work. Okay, so I could have typed it in just as it was given. You'll see this is a vertical line going through the number 4. But I could have also typed it in just like I did a moment ago where I said r equals 4 divided by cosine, and you still get the same graph. So this will be a vertical line. It's a vertical line. Sorry, I'm trying to get one with the arrow on both sides. That's going to go through the value of 4. So I just missed slightly. Let me move that over, just like that. And so that would be my equation right there. Or my graph, rather. There's my equation. This would be my graph. All right, so now I want to give you your first DOL. I'll let you graph r equals -4 cosine theta and see which graph appears to be correct. All right, let's move on to example 2 now. It says use symmetry to graph r equals 1 minus 3 cosine theta. Well, I'm actually going to start with technology because that's how we usually graph, and then I'll talk over the symmetry. So we have 1 minus 3 cosine theta, and we get this graph that's called a limicon. This graph right here represents a limicon, and I'm going to just do this so I can keep my units the same. I'm just going to zoom in. There we go. I think that'll make it a little bit easier. And you can see this is a limicon because it has that inner loop. And to get this graph looking right, what I need to do is copy this portion of my equation, and I want to fill it in on this R1 right here. So when I fill that in, oh, I need to put a 1. That's what this is right here. Exchange the theta with a theta 1, and the R needs to be a R1. So I got it. What's going to happen, let me start at 0, is it's going to show you how it graphs. This graph starts on the left. So normally cosine, we think of starting on the right and moving cosine x, so it starts on the far right. But this time we have a negative cosine. So it would start, you would think -3 units, but it doesn't because of this +1. So what happens mathematically is that if I just gave you kind of like a brief little table here to show you kind of the math of what's happening here. When theta, I'll put theta here, and then 1 minus, now let me do cosine, what cosine theta would equal, and then I'll show you what 1 minus 3 cosine theta would equal. 1 minus 3 cosine theta. Okay. So here's the idea. And I'm going to basically use unit circle values because I know these off the top of my head. In case you don't, let me just add these on here so you can see that I'm not just making up numbers as I go here, that there is going to be a system to my madness. So what I'm going to do is use this unit circle, and I'm going to remind myself that cosine is the x. And so when I'm looking at a theta of 0 degrees, the cosine value there is 1. So I have 1 minus 3 times 1, which is basically 1 minus 3, which is a -2. And so when theta equals 0 degrees, and I need to change my mode now to degrees. You know what? Since this is not saying anything, I'm gonna switch gears here. Let me erase the 0 and just work in radians, so I don't have to switch to calculator mode. I'm gonna switch this just to radians. So we're now gonna be dealing with radians. So at 0 radians, the cosine's 1, and so the math still works out. That means when my radians are 0 over here, 0, I need to move 2 units to the left. So why? Because instead of being positive, it says reflect 2, so it goes that way. Now I want to jump over to the radian pi over 6. So what happens at pi over 6 is that the cosine is the square root of 3 over 2. That's the value for cosine. And so I'd plug this in, and I'd have 1 minus 3 times square root of 3 over 2. 1 minus 3 times the square root of 3 all divided by 2 now. I just multiplied the cosine by 3. And so that is also going to be a negative value, and that's going to be, if I had pi over 6 here, pi divided by 6. That's what that value is right there, -1.59. And so at pi over 6, I'm moving away from it, that amount of values. And so that's how it kind of works going around. Now the symmetry, as you can see, this is cut along the polar axis because it's cosine. Anything with cosine is going to get cut by the x-axis. And we could go all the way around. I'm going to do just one more point. I'm going to do pi over 4. At pi over 4, the cosine of pi over 4 would be the square root of 2 over 2. So if I plug this in, I would have 1 minus 3 square root of 2 over 3. And so that's how you're going to get your values. Long story short, if you go all the way around, you just kept plotting your points as you go. On all of these thetas, we're going to end up with negative values up until we get, when you start getting positive radiuses, is whenever this value here becomes -1 or greater. Because from then on, the math here works out and you have a positive radius. And so that's when the values start actually falling. So at this stage, this theta, where's the theta? Right here. It's approaching 1 whole pi. By the time we get to 1 whole pi, the radius will be a value of 4. Let me show you. When we get to pi, the pi here, the radius is 4. And so it's 4 units directly to it. So that's how you have an inner loop. The inner loop is when this value is turning out to be negative and it's reflecting all these values across. The positive is once we're dealing with a radius that are positive, but I'm dealing with these thetas, so I'm moving towards it on the left. So that's how the graph ends up looking, just like that. All right, so now I'll let you graph one and see what this Limicon ends up looking like when you graph this. All right, before I move on, I thought of something I didn't share there. And it's this: when you deal with these Limicons, the greatest value out here, this is kind of how polar works differently, is going to be the combination of these two numbers, because cosine's maximum is 1 and its minimum is -1. So the farthest this graph will ever get, doesn't matter if you have positives or negatives, will be the absolute value of these two numbers combined, which 1 plus 3, again, absolute value, ignore the negatives. 1 plus 3 is 4. That's the farthest this graph ever gets away from the origin. This inner loop will be the distance between the subtraction when you subtract these values. So 1 minus 3, again, just kind of think of absolute values here. Just the 1 minus 3 will be 2, or -2, you could say, but it'll be 2 units away from the center because of the subtraction of those two values. Cosine means it's moving left and right. Because it's a negative cosine, it's on the left side of the graph. I meant to mention that earlier and I forgot. So now let's take a look at example 3 here. It says the area lit by 2 lights that shined on a stage can be represented by the equation R equals 1.5 plus 1.5 sine theta. Suppose the front of the stage faces due south. Graph the polar pattern of the 2 stage lights. Okay, so think about if you're at Skyline and there's a play in the auditorium or something. And so the front of the stage, it says faces due south. So here's our stage. Let's just imagine this. This is the stage. And you have all these seats out here in the auditorium. So these seats, if I took more time, they should all be arranged the same size, which I'm not getting right now, but let's just say they were. All the same sizes going across, and so on and so forth. So you have all these seats going out here. Now, what this is saying is that the light technology, people use polar equations. Now, why is that? That's because with polar equations, we're going to be able to light up the stage without lighting up the audience. If you think about going to the movie theater, they turn it really dark, but you have a really bright light on the screen. That's because it's easier to see if you're sitting in the dark. But the stage, or in the case of the movie theater, the screen is projected with a really bright light. It's easiest to see that way. So that's the idea. So when I look at this picture here, it's 1.5 plus 1.5, whoops, I forgot the plus, sine theta. That's my equation. And what I'm going to do is copy this equation, and I'm going to replace this one. And I'll just put a 1 after the sine. And so what this means is if I were to play my angle and just see it graphed all the way around, you can see that what's happening is in this situation, this is lighting up the stage, but it's keeping as much of the audience in the dark as possible. So it's a setting up a light. Let me kind of now put an axis on my graph. If this, you would set it up to where if this is your axis here, that so much of the stage is getting lit up, but that the audience themselves are staying for the most part in the dark. Obviously, you're getting a little overlap of light, but this is a pretty good little way of keeping the audience in the dark while keeping the stage lit up so that you can see the play or whatever the performance is on the stage really well. So what I just did here is I graphed it, just like I was told to do here in part A. And also, what we did was we described why you would use this. It would be to light the stage while keeping the people or the audience in the dark. It makes it easier, again, for the audience to see. It's more effective for that. This would be the two lights. You know, light usually comes down from, if you've seen an auditorium before, it's circular lights, and they overlap and kind of shine in that way so that the stage is really bright, whereas the audience is kept in the dark. That's the idea there. By the way, this would have symmetry at pi over 2 because it's sine. Sine is y, so it'll be graphed on the y-axis. Because this sine is positive, it's graphed upwards. If it had been negative, everything would have been opposite. Everything would have been the opposite if it would have been a negative. But it wasn't, it was a positive. That's why it was up on the positive side. This right here is called the cardioid. It looks like a butt or a heart. So a lot of people, when they see sine, say, oh, it kind of looks like a heart. So you do cardio to strengthen your heart. The reason it's cardioid is these numbers are the same. They're both 1.5. That's why it looks like kind of like a butt crack or a heart. If it's turned to the side or any other direction, most students say it no longer looks like a heart to them. Now it looks more like a butt. And so that would be the graph. All right, here's DOL for 2 for you. You can now graph this one and answer the questions accordingly. If you've had enough time to read it, I'm going to move on. If not, just pause the video until you finish reading it. Here's your answer choices. Pause the video until you've got your answer. All right, so now we're going to go get into a little bit more of the algebra here. It says use symmetry, zeros, and maximum R values to graph R equals 2 sine 2 theta. So I'm going to come to my calculator here. And I'm first just going to graph it. R equals 2 sine 2 theta. And what we see is we have what's called a rows here. And I'm going to also copy this and place it in this location here and just put a 1 after. And so we have this full graph. This is a rows, and I want you to notice it has what we call 4 petals. So as we start graphing, this is sine, which means it should be cut in half at pi over 2, but we'll see with the symmetry, it's actually different because of this transformation. So let me start with the symmetry here. Symmetry for sine theta, we think of the symmetry equaling pi over 2. But this is 2 theta. So 2 theta would equal pi over 2. And if you solve for theta by dividing by 2, we get that pi over 2, then dividing by 2 again. It's kind of like saying pi over 4 or pi over 2 divided by 2, or 2 times 2 down here. It's the same idea. So you would end up with pi over 4. That's going to be my symmetry. And looking at the image, you can kind of see that that's where it's cutting this petal in half as well. So I know there's multiple symmetries, but that would be pi over 4 would be the most accurate representation. Symmetry, the pole, pi over 4. Let me write that in there, pi over 4. Okay, so now if you want to know what's the maximum R value, well, the maximum R value is the farthest this graph ever gets away, which happens to be the coefficients. Again, if there were multiple numbers, it would be the absolute value of all the numbers combined together, which in this case, we only have this coefficient. This 2 is dealing with the petals. The answer will be the maximum R value will be 4. No, I said 4, I'm sorry, 2. Because the greatest sine can ever be is 1. So the maximum R value is 2. Kind of going out of order here. And it says find zeros. Well, zeros are whenever sine equals 0. And according to the unit circle, sine equals 0 at 0 and also at pi. As you think about unit circle, sine is y. At 0 and pi, we have 0 and pi, the y value is 0. So this graph will have zeros. You got to take into account the transformations though. So normally it would be at 0 and pi, but because we're working with 2 theta, I want to put a 2 there and solve it. So a 2 theta at 0 and pi, so I'll divide by 2, divide by 2. This time we will have zeros when at 0, at pi over 2. And because I've cut everything in half, this would have twice as many. So I'd keep going around. There would be another one at pi and another one at 3 pi over 2. So another one at pi and another one at 3 pi over 2. If you just go around. Once I saw the pattern, they're having a 0 every pi over 2. I just continued it on. These would be my zeros. There. All right, so let's check this out. If we're correct, this graph should equal 0 at this point. So when it's at 0, notice the R value is 0. At pi over 2, pi divided by 2, we got an R value of 0. At pi, pi, we're at 0. And again, if you just check the angles here, on the pole of 0, we're at 0. Pi over 2, the graph's at 0. At pi, we're at 0. 3 pi over 2, we're at 0. So you can see that those values are, in fact, graphing just like we thought. All right, let me press play now here. And you can see this. Something that's interesting, I think, with polar, or with polar, but with flowers, is that if it's an even number on the theta, it's actually always going to double the petals. So notice I have a 2 here inside with theta. That created 4 petals. If I would have put a 3, it would have only been 3 petals. So odd numbers just stay as they are. That would be 5 petals. But even numbers double. So 6 will turn into be 12 petals if you had a 6 there. And so you can see how this graphs all the way around. So I think that's pretty neat. The front coefficient, if you're wondering, that extends how far out the theta goes. So now I'll change these. I'm just copying my equations here to make sure they're identical, and you can see it trace around. Something else that's pretty neat is if you polar graphs, you can start doing a lot of creative work with. So for example, I'm going to make this r is less than or equal to, and I need to make this an absolute value for this to show me all my petals, right? Okay, so r is less than or equal to 5 sine, the absolute value of 5 sine 6 theta. And so I filled in my flower. And now what I'm going to do over here is I'm going to basically, whoops, that's not what I wanted to do. I'm going to copy this. But I want to, you know what? I think I actually have it down here. Yes, if I go to distance, I do. I'm going to hit this one. Pull this up and make my equation match. It's 5 sine 6 theta. Okay. And I'm going to show it this graph. Let me start at 0. And what's going to happen is this is where you can see the cool artwork go. As I press play, we already see the whole equation graphed here. As I press play and as the theta is increasing, you're going to see this dot draw out, but I'm going to leave it as if I was drawing from that point. So when I press play, you can see the purple filling in. And you can see the order of where it's graphing as it moves along. I think that's kind of a really neat tool here. And not only that, it makes a pretty cool looking flower that we're not used to seeing with mathematical graphs. We're used to seeing a lot of straight lines and things that just don't seem as creative. But I think this is pretty cool how it works. And we're about to have a now purple petaled flower or rose with orange filling. It's pretty neat, if you ask me. But anyways, back to this problem. Here was our graph. The maximum R value was 2 units out. That was the maximum. And by the way, the minimum would be -2. The zeros occurred at 0, pi over 2, pi, and 3 pi over 2. All right. Let's let you try one here. I want you to determine, there's a little bad formatting. This needs to be a theta here. I want you to determine what theta, right there, what would be true here, the maximum R values, what this would be symmetric to, and is that it? Yeah, that's it. Deal well, number 4. Okay, I want to remind you that with sine, we're always symmetric to pi over 2. However, with the transformation, you can be symmetric to other locations as well. So this graph, you should be symmetric to a different pole as well. If you solve for theta equals pi over 2, you would get an extra pole in there. All right. Now let's talk about some other types of graphs. It says here, identify the type of curve given by r squared equals 8 sine 2 theta. Now, this is one, I'm just going to refresh my calculator here, and I accidentally saved it, so I need to open up a new one here. Let me open this up. I don't think Desmos, unless it's updated here, will graph this. No, it's saying it will not graph this. 8 sine 2 theta. Notice that is not graphing. So what you'll have to do is you'll have to solve for r by saying that r equals the square root, because the opposite of a square is a square root of 8 sine 2 theta. And so that's actually what I'm going to graph. So let me take away the square there. And I want to put this in square root. So I'm going to highlight it, press the square root button, and hopefully, no, cancel it all. Sorry. I'll just have to type it in. 8 sine of 4 theta. No, 2 theta. I'm sorry, 2 theta. And I'm going to copy this and paste it on this equation right here. But I'm just going to put a 1 after the theta. So now we have what's called a lemniscate. Now the values are a little bit different. They're not quite as easy. It's not going to go out to the 8th circle. It's actually going to go out to the square root of 8. So the farthest this graph will travel out is technically 2 square roots of 2 if you simplified the square root of 8. That point right there would be 2 square roots of 2 away. Now how did I get there? Let me show you. If I go to this maximum value here, as you can see it's on the pi over 4. This number right here, if I wanted to get there exactly, I'd say pi divided by 4. Notice that's that point right there. This value, the x and y are 2 and 2. And if you wanted to find how far is that radius, you'd take the square root of x squared plus y squared. You do the Pythagorean theorem, but I have the value written right there. That is the square root of 8. Notice that is the square root of 8, which you could reduce as 2 square roots of 2. So you notice those are all the same. So that is the maximum r value here. Let's says, what about the symmetry? Well, because this is sine, this would have symmetry at pi over 2. Because it's sine, we know it has symmetry at pi over 2. But it also, since it's sine of 2 theta, you would also have, if I wanted to solve for the other one, 2 theta equals pi over 2. And again, when you divide by 2, we would get pi over 4. So this has symmetry both at pi over 2 and the pole pi over 4. The zeros, where would the sine equal 0? Well, sine equals 0 at 0 and also at pi. So we normally think of that being at 0 and pi. But again, this is 2 theta. So when I would need to divide by 2 here. And so we would have zeros at 0, pi over 2. And if you want to keep going around, these you can see they're happening every pi over 2. So it'd be at pi again and then 3 pi over 2. You would have zeros. So all these values, if I plug them in, the r value that spits out would be a 0. So let me try pi over 2. At pi over 2, the r is 0. At pi, we're getting 0. And at 3 pi over 2, 3 pi divided by 2, we're also getting 0. So you can see how that's all working out. And the maximum, what we just said, was the square root of 8. That coefficient. The maximum would be the square root of 8. And they do this absolute value of r here, square root of 8, which happens to be 2 square roots of 2. This is a lemniscate, by the way. Lemniscate. Actually, it might be a K. I'm blanking all of a sudden. You know, you spelling these words, they're not English words here. the spelling on these. Let's go back here. Limnoscate. No, it is with a ski. And it says you pronounce it limnoscate. I call it limnoscate because it looks like an 8. All right. B, let's try this one. R equals 2 theta. So R equals 2 theta. And we're going to get our spiral here. R equals 2 theta. So this means whatever. All right, sorry, I had to pause there. I'm not exactly sure where I left off, but what I want you to see on the spiral of Archimedes is what we call this one. What's happening is the R value itself is always going to be twice the angle. That's just how the math looks. It says the radius will equal twice the angle. So as you start at 0, 2 times 0 is 0. But here I have listed, oh, I need to put the 1 there. Come on now, 1. If theta is 3 pi over 2, that's this decimal. Notice the R is just twice that. That's all that's happening. So whenever theta is 3 pi over 2 right here, the angle 3 pi over 2 is 4.7. What this means is from the distance from it is 9.42, as you can see right there. Well, let me give you an easier one, pi. Pi we know is 3.14. What does that mean over here when we're at the angle pi? Can't see pi, there it is. Zoom out just a tad. So when we're at the angle pi, on the pole pi, I should say, you are 6.28 units away from, or negative 2 pi in terms of x and y, away from the origin. That's how it looks. It's 6.28 units away. So it just doubles all the way around. And this one's really neat if you just extend it out. Let's graph it for a little bit longer and zoom out and zoom back in, zoom out. You can get someone hypnotized if you're not too careful here on this one. I think that's enough of that before we don't get sick or anything like that. So anyways, another cool looking graph in my opinion. This one would have no maximum R values, no symmetry. It doesn't have sine or cosine, so there's no symmetry, no symmetry, no maximum R values. Zero. Whoops, let me write the word 0. 0 at 0. It's the only 0 is right there at the very start. Oh, I don't think I named that one. That one's the spiral. Spiral of Archimedes, which I will refer to frequently as just a spiral. And so now I'll let you graph this one and decide if that's a cardioid, limnoscate, Limicon, or a rose. All right, general overview. Cardioid is going to look like a heart or a butt. Limnoscate is going to look like an 8. Limicon is going to have an inner loop. And a rose is obviously going to look like a flower. So ACP problems, how might this look? Or release questions from the past is you are given equations and you just have to match up with what the equation would be. So a cardioid, if we try these, the theta equals, if you remember, that is a graph across the pole. That means it doesn't matter what the radius is. It's just going to follow the pole 2 pi over 3, which would be a straight line. So it's not going to be A. A is a straight line through the pole 2 pi over 3. Let's try the other graphs. R minus 2 equals 2 cosine theta. Oh wait, I already had the theta. 2 cosine theta. There we go. This right here is a cardioid. It looks like a heart or a butt, if you want to think of it that way. And so you need to do cardio for both of those two things. So this would be that equation. Let's just go ahead and finish off and see what the other ones are. 2 sine. There we go. Minus 1. What would that resemble? This has the inner loop. We would call that a limicon. Let me write this in. This is a line through the pole 2 pi over 3. Okay, the green would be a, or excuse me, the C will be what we called a limicon. Oh, accent there. And then 2 theta, this was the spiral we just saw a few moments ago. That would be the spiral. Now that we have all these listed, we can solve the other problems. So which polar equation produces the limicon? Well, it would be C. That equation had the inner loop. And that was because the two numbers are not the same here. Whereas on for a cardioid, your two numbers are the same. And that's why you don't have that inner loop. And finally, the spiral was D.